Okay, so we are very happy to continue uh, application of classifications. I just have to kill one window here. Got it. And now it others. Thank you.
All right. So today I'm going to talk about some of the basics of K-theory. Just in case you're not super familiar with this, hopefully it'll remove some of the theory around it. So the starting point is equivalences of projections. So let's start there. So projections, by which I mean self-adjoint idempotent in the C-star algebra. So in A. So just some terminology. So first of all, they are Merritt-von-Neumann equivalents. And I'll write it like this: P sim Q. If there is some V such that on the one hand, V star V is P, and the other hand, V star is Q.
Do you assume that A is stable?
No. Not yet. It's P, V star is Q. So this B is a partial isometry. Which, I mean, equivalently, V star, so V star V is V. Take that as definition of partial isometry, if you like, with support P and range Q. All right, so support P, I just mean V, P, is V, range Q, Q, V is V. Okay, so that is the first notion of equivalence of projections. Second notion is unitary equivalence. So projections are unitarily equivalent. And I'll write P sim U Q. So at the moment, I'm not assuming that A is a unital C-star algebra. So what I wanted to find this to be that there is some unitary in the minimal unitization such that P is U to U star. So if there is a unitary U in a tilde. So again, this means the minimal unitization. So it's just A if A is already unital, so such that P is U star. All right. So Merritt-von-Neumann equivalence, then unitary equivalence. The third notion of equivalence is homotopy, which just means it'll be apart from one of the equivalents. Projections are homotopic. Which are, P sim H Q if there is a non-continuous path consisting of projections. So in the projections in proj A, I just mean the collection of projections in A from P to Q. So the basic proposition, which I'll now state, but I won't get into the proof. I mean, it's not hard, just for reasons of time. Is that first of all, okay, these are equivalence relations.
Go ahead.
Oh, okay, right. The second is that they are successively stronger equivalence relations. So homotopy implies unitary equivalence, which implies Murray-von equivalence. All right, so to show that homotopy implies unitary equivalence, what you do is you show that close projections are unitarily equivalent. It's a little functional calculus argument. And then you just so you can chop up your path into small bits where you get one state to the next is unitary equivalence, you get a chain of equivalences. So basically equivalent to the last. Okay, so that's how you prove this first implication. The second I won't get into, but what I will say is that the reverse implication is true if and only if, in addition to P being equivalent to Q, 1 minus P is equivalent to 1 minus Q. I see, there's a problem with the camera.
Yeah.
Okay, right.
In a minimal unitization, I suppose.
Yeah. So in all right. And then the third thing is that, okay, these reverse implications are not true in general, but they're stably true. So, reverse. Stably true. Okay, I mean, all right, so this is a bit of informal what I'm saying here. What I mean is that if, for example, P is unitarily equivalent to Q, then in the 2x2 matrices, they are homotopic. So P being unitarily equivalent to Q implies that P 0 is 0 is 0 is homotopic to Q 0 0 0. And similarly for the other one, if they are Murray-von equivalent, then these are amplified in 2x2 matrices are unitarily equivalent. The proof of this fact that I wrote there, it's a neat little argument using what's called Atiyah's 2x2 rotation trick. I just don't have time to get into it, but if you, it's a nice little easy argument. All right. So, and as I said, it's not true in general. If we don't amplify one, so let's see, for this implication to show that this is not true in general, I think there is an example in the in 2x2 matrices over continuous functions on the 3 sphere. There is an example that shows this doesn't hold. This one is a bit easier to show. So let me show you that. And this
You said the inverse implication.
yes. What?
For example, the inverse implication.
Yes. Sorry. Yes, exactly. The counterexample for why you need to pass to the 2x2 matrices. Okay, let me show you why this reverse implication does not hold in general. So you just look at B of H. So take any projection P in B of H that has infinite dimensional range. So H is infinite dimensional Hilbert space. So with infinite dimensional range. So then they will be Murray-von equivalent. You know, I take non-unitary isometry that from H onto the range of P. This will give me a Murray-von equivalence, but they're not unitarily equivalent. Because the only thing that's unitary equivalent to the unit is the unit itself. So this I'll get to the. I'm going to slowly get to the definition of the K0 group. Right, the starting point is this notion of equivalences. We'll get to the definition. It'll take a little time. Before we get there, I want to introduce some terminology that I was tossing about last time. So now I'll explain what they mean: stably finite, purely infinite, that sort of thing. So a C-star algebra. So A.
Is this implication true for stably finite C-star algebras? Because for fundamental algebra, which is traceable or finite fundamental algebra, it's true. So
I think maybe for stable rank 1 C-star algebras, but I don't know about stably finite in general. I don't think. Yeah, I think stable rank 1 means something like this. Okay, so but now to explain the terminology we were just using. So A is finite. All right, so if no projection can be equivalent to a proper subprojection. So if whenever, well, yeah, okay, so whenever P is subprojection of Q, meaning, for example, that QP is P, and Q is equivalent to P, we must have P in fact equal to Q. And it's stably finite if not just A is finite, but any matrix algebra over A is finite. Stably finite. Means that Mn of A is finite for every n. Wait, so I mean, what this shows here is that B of H is not finite, because we have a projection equivalent to a proper subprojection. So B of H is not finite.
So what's the relation between this finiteness and
Finite dimensionality.
other kinds of finiteness?
I think it has to do with this sort of example. I mean, this is a projection with infinite dimensional range. This is what this kind of situation you want to avoid. So it has to do with finiteness of the projections.
So is it finite dimensional? C-star algebra automatically finite?
Yes, it's if that's what your question is.
Not the other way around. Can show us an example of finite in your sense, which is not finite dimensional?
Yes, absolutely. I see. That this is your question. I mean, this is a weaker notion of finite dimensionality of the C-star algebra. Yeah. So as I was just saying, B of H. I mean, I will give lots of examples. Just know stably finite algebras. So just to write what I just said, so B of H is infinite. So infinite just means not finite. Or equivalently, there is an isometry that's not a unitary.
But if H is finite dimensional Hilbert space, then it's true.
Yes. Yeah. Thank you. Right, so in fact,
Do you assume a separable or not?
I guess all the time I'm never going to talk about non-separable Hilbert spaces, but even if it's non-separable, this is still.
Yes.
Yeah, but I will never talk about non-separable. Right. So in fact, it's even more than infinite. It's what's called properly infinite, which means you have two isometries with orthogonal ranges. But let's move on there. One remark is that finite does not imply stably finite in general. So Mikhail Rhythm has some very dramatic examples. There's a simple C-star algebra A, such that A is finite, but 2 by 2 matrices over A is infinite. In fact, properly infinite in the sense I was just describing. So there is a simple A.
So here by stable or stably, you mean
After passing
tensoring to pass into matrices?
Yeah.
What about tensoring?
I think it should be equivalent. It should be equivalent. should be equivalent.
Okay.
Yeah.
She's, okay.
So there's a simple simple finite A. Such that M2 of A is what I just briefly described in words properly infinite. Okay, and then just one bit of terminology, then I'll get to lots of examples of stably finite C-star algebras. This another phrase that I was talking about last time is purely infinite. So what does that mean? So the strongest notion of infiniteness or simple C-star algebras. And infiniteness, I mean, in the sense of this theory of projections. I'm saying this for simple A, the notion of pure infiniteness makes sense also for non-simple C-star algebras, but there are a bunch of different ways you can define pure infiniteness. It turns out they're all equivalent for simple C-star algebras, and then it's a question of which one you want to choose in the non-simple case. So let's not worry about that, and let's just restrict to simple C-star algebras. So it means that, first of all, A is not the complex numbers, and if you give me any two non-zero positive elements, I can get it from one to the other via like a Murray phenomenon. So there's some X such that XAX dies B. Okay, if you consider it a little exercise, I mean, this does imply that the algebra is infinite, so it's not finite. Okay, so here's the theorem that I will state that will give us lots of examples of stably finite algebras, which is that being for a simple C-star algebra, being stably finite is equivalent to having a trace. These two are equivalent. But the theorem Blackadder, I mean, okay, bunch of it's Blackadder, Handelman. Harup, and also Blackadder and Kuntz. Which is that if A is a simple and exact C-star algebra, then as I said, stably finite is equivalent to the space of tracial states being non-empty. So if A is simple and exact, and
So did you define that?
I did not. This is a good point. Maybe I should. One way is, remember last time I defined nuclear as being having this completely positive approximation property, which meant that for a C-star algebra A, the identity map was nuclearly approximable. So we can find some completely positive map down into some finite dimensional C-star algebra and some completely positive map finite dimensional and some completely positive map going back up, such that on a fixed finite set, this commutes up to epsilon on this set. All right, that's what it meant to be nuclear. Exact is a weakening of this, where instead of the identity being approximable in this way, we want there to be some embedding of A into some B of H, such that this holds. So there is a representation of A on B of H. Yeah, I think so. Let's say it. But yeah, there's a fifth representation onto B of H, such that we have this approximation happening for any finite set and any epsilon. That's one way of defining exact. Equivalently, you want the tensor product to be to preserve short exact sequences. I think the minimal tensor products.
Minimum, yeah.
I think, right. So in other words, if you have a short exact sequence of C-star algebras, J, A over J, then B is exact. If for any such sequence, if I tensor with B, I still get a short exact sequence.
Okay, so this is some kind of flatness then?
Exactly. Yes. Yes. You know, so it's Kirchberg who came up with this notion, and so you know, if you don't know, Kirchberg passed away last year, but I remember I was sitting with him and my PhD supervisor Simon Barstow at some point in Nottingham, and he was explaining why he chose the terminology exact instead of flat. I cannot remember what the reason was.
Oh, but I think we might very easily decipher it. You see, when you look at the usual algebraic tensor product, then it is automatically right exact. Okay, it's always right exact. So exactness really means this left exactness. Okay, but I think when you go to C-set tensor product, somehow things are on the wrong side, and
I see.
and that's why it's exact is a very good name, because it's immediately clear that you preserve exact sequences.
Yeah.
But flatness is in algebra, it's really related to ensuring left exactness. Yeah, left exactness, exactly. Because kernels are not preserved in general. Co-kernels always are.
All right.
Opposite to cotensor product.
Flatness is left exactness.
Yes. Yes. Because right is automatic.
Yes.
Yeah. Just like with cotensor products, the other way around. Yeah. Injectivity is preserved for cotensor products, survivability is not. Yeah. So co-flatness means right exactness, flatness means left exactness. So, and here I don't remember, but I remember we were working on it, Ludwig, I remember, and it turned out that when it comes to minimal tensor, yes, I'm pretty sure. This is why we can do all these comodular algebra stuff and so on. For minimal tensor product, you have left exactness. Surprisingly, even though it's a tensor product, not a cotensor product, what you have to ensure is right exactness.
I see. All right.
That's why I think.
Yeah. Okay.
I would choose back. I would choose it.
Yeah. Fair enough. All right. So, okay. I mean, I hope that's, but in fact, this is, you can even remove this assumption. I'll comment on that shortly. So simple and exact, then A is stably finite. If and only if the trace space is non-empty. So just to remind you, this is my notation for the set of trading states, which I'll talk about in some detail next time.
May I comment about this flatness?
Yeah.
If I remember well, the problem is that this minimal tensor product is not even right exact.
That's exactly what they're saying when you browse.
Okay.
Yes.
Good.
Yeah, it's left exact. Right. So you can remove this assumption, but then you need to, instead of talking about traces, you need to talk about quasi-traces. So part of this work is to show that for exact C-set algebras, every quasi-trace is a trace. So that's why that is there. By the way, I mean,
Quasi-trace is what?
it's a weakening of trace where you don't even have linearity holding in general, only on commuting pairs of elements somehow. So I do not want to get into this at all. Everything I'm going to talk about will be exact, except I will mention a couple of non-exact C-set algebras today. Hopefully I'll get to it, but let's not go down this road. Right. By the way, so one of these directions is very easy. So the meat of this is showing that if you are stably finite, then there exists some trace. Somehow you have to construct this trace. The other direction is easy because if we're a simple C-set algebra, then every trace is faithful. So if we have P less than or equal to Q, then we have tau. The trace is, so if there is a trace, is trace of P plus a trace of Q minus P. But we're assuming that these are equivalent projections. So by the trace identity is, trace AB is trace BA, so trace V star B is trace BB star. So these have the same trace. So this is trace Q. Well, I mean, this is trace Q. So this has to be 0. Okay, so but it's faithful because we're assuming simplicity, so therefore Q has to be equal to P. So that direction is easy. So this gives us a source of examples of stably finite C-set algebra. So anything that's simple and has a trace. So for example, the n by n matrices with its canonical trace, this is stably finite. The Jiangsu algebra is stably finite, it has a trace. simple AF algebras, UHF algebras, all of these ASH algebras I was talking about last time, all of these are stably finite because they have traces. Once they're simple, you can make it certain.
Sorry, can you tell me again why this trace of Q minus P is zero?
Right, so just because trace, it's the equation of real numbers, so trace of Q equals trace of Q plus trace of Q minus P.
Yes.
So just bring this to the other side is zero.
Faithfulness.
Painfulness, okay,
Yeah, yeah.
painfulness, yes, okay, thank you, yes. Yes, yes.
That's why simple.
Yeah.
Pairing.
Could you remind me about this threshold state?
Yes.
Traces are Morita invariant.
Yes.
What about threshold states?
That's a good
I forgot.
question, but I mean,
Threshold states.
but a Morita equivalency to algebra might not have any trace states, the complex numbers and the compact operators. There's no trace states on K. So the cone of traces is invariant, is what you can say. No. All right. Okay, so that's why we have so I hope this explains this terminology that I've been using, stably finite, in terms of classification. Just think it's the algebras that have traces, because all of the algebras in this category are simple. But in fact, there is this dichotomy. So the only other possibility is pure infiniteness as far as classification goes, because of this theorem.
No,
So a simple separable, simple exact set stable C-star algebra. So Z stable, let me just remind you that so Z was this Jiangsu algebra that I mentioned last time. It's the unique classifiable C-star algebra with the same Elliott invariant as the complex numbers. So the K0 group of Z, which I'll get to eventually today, is the integers, and the K1 is zero. So and this is what Z stability means. So such an algebra is either stably finite or purely infinite. So either it has a trace, and if there are no traces, it has to be this very strong notion of infinite. And this is not obvious. I mean, there's no reason that it's something that's not stably finite. It should automatically be purely infinite. It's something that is there, stably finite, or purely infinite. Okay, so right. So let's just recap where we are. So first of all, I stated these different notions of equivalences of projections, and I just explained this terminology that I've been throwing about. I hope this at least clarifies it a little bit. So now let's work towards defining the K0 group. So the first step, the next step towards that is to define the Murray-von Neumann semigroup. And from this, we will do the growth and deconstruction and get the K0 group. So definition. The Murray-von Neumann semigroup group A, C-star algebra A is denoted by B of A, and it is the set of equivalence classes of projections in matrix algebras over A. Oh, yeah, I could also define it in terms of the stabilization. I'll get an isomorphic group. And here by equivalence classes, I mean with respect to any of these notions of equivalence relation, because what we observed is that they are stably the same thing. So in M infinity of A, it doesn't matter which one I choose, it gives the same. So this could be this or this or this equivalence classes. Right. So that's what it is as a set, but I call it a semigroup, and the addition. So with I guess it's a monoid even. So with define P plus Q to be the equivalence class that we just diagonalized, 0, 0, Q. Okay, so this is a abelian monoid where the unit is the cost of the zero projection.
So this M infinity of A is a non-unital star algebra.
Yeah,
I think that
it's a local Caesar algebra.
local system.
Yeah. But you're right. This should be made clear because I've only defined what these equivalences are in Caesar algebras, but in local Caesar algebras is enough.
What if M infinity is replaced by tensoring by compacts?
It's the same thing. It doesn't matter. Okay, get exactly the same object. I mean, this needs proof, but it's functional calculus essentially.
There is no way to put a ring structure on this. Tomek will ask this
Sorry, say again. Please.
structure on this K groups.
Which kind of
If A is non-commutative, you don't.
ring structure? I see. Yeah, no, only in the commutative case. Only in the commutative case we have a ring structure. Okay, so equivalently, you could define this as the semigroup of isomorphism classes of finitely generated projective A modules. I guess right A modules say. I just want to mention this because at some point, maybe next time or next couple of weeks, I'm going to tell you about the Kuntz semigroup, which is defined similarly to VFA, except in terms of positive elements instead of projections. But another way of thinking about it is if instead of finally generated projective A modules, you take countably generated Hilbert A modules, you get this notion of the Kuntz semigroup. It's a very kind of natural extension of, but we'll get to this later. All right, let's have some examples of some possible semigroups we get from Caesar algebras. So first of all, the semigroup associated with the complex numbers is the same as semigroup associated to any algebra of n by n matrices. It's the same as the compact operators, and it's just the natural numbers. Let's say 0 is natural number. So this is just by sending a projection to its rank. The two matrices that are projections are equivalent in any of these notions, precisely when they have the same rank. So this is an isomorphism onto the natural numbers. The semigroup associated to continuous functions on a compact Hausdorff space is by the CS1 theorem, maybe with this observation in mind, it is the set of isomorphism classes of vector bundles over the space. So in particular, the semigroup associated to continuous functions over the two sphere, there are two vector bundles that generate this semigroup. It is the trivial bundle and the bot bundle, which is a non-trivial line bundle over the sphere.
Do you assume that X is compact?
At the moment, yes, but I will immediately after this talk about locally compact bot bundle. So this is S-ways. But I mean, I'm just telling you this as a fact, which you may be familiar with. Okay, right now let's get to a locally compact algebra. So let's look at C0 of X. And the point I want to make is that is just 0 if X is locally compact and connected. because the function that assigns to a projection its pointwise rank is continuous. So at the point of infinity, it's zero, has to be zero everywhere. Okay, so now let me give you a sort of maybe interesting example. So this would be one of these sub-homogeneous C-star algebras that I mentioned. Sub-homogeneous, it's going to be a C-star algebra of continuous functions from the interval into matrices, but I'll put some boundary conditions.
Sorry, but you said something which maybe more difficult because you are saying that this semi-group is zero.
Yeah.
But what you said means only that you cannot apply this rank to obtain some homomorphism to something non-trivial.
Yeah, that's true. That's true. That's a good point. That's a good point. Yeah. But I guess what I'm claiming is that there are no non-trivial projections in the C-star algebra. Yeah, you're right. Yes. More difficult. It's a good point. But yeah. Good point. Okay, so let me define for you this C-star algebra. So it's continuous functions from the interval into the 2x2 matrices, such that at 0, it's of the form A0, 0, A, let's say, and at 1, it's of the form A0, 0, 0. And A is a complex number. So it's the same A on both sides. Right. So this algebra, I claim, also has no non-trivial projections. Do you buy this? I mean, again, it's a rank argument. So the rank of any projection in here has to be constantly 0. Why? Because the rank at 0 is twice the rank at 1. So the only way that happens is if A is 0. So the constant rank of this, any projection in here has to be 0. So it's the 0 projection. So this has no non-trivial projections. And in fact, even if I pass to a matrix algebra, I still get no projections. So if I take the n by n matrices over this A, it's going to have a very similar description, except instead of being into M2, I'll live in M2n. And instead of A being a complex number, I'll have A living in Mn. So I'm claiming that as a fact that Mn of A is isomorphic to an algebra of the same form, only difference being that A is now an n by n matrix. So for the exact same reason, neither does Mn of A. Or any n. So this is an example of what's called a stably projectionless C-star algebra. I mean, these are quite important in the classification program, but as I said, I'm only going to be talking about non-unital things. I mean, no, this is very much non-unital. There's no identity in this. I mean, it's very, very non-unital. So in this case, V of A is 0. And it is, as I said, stable projections. All right, so that's it for examples for now. Let me tell you about some properties that this functor that sends from C-star algebras to semigroups has. Some of the properties. Well, one of the properties is that it is a functor. So properties phi. First is functoriality. So if I have a star homomorphism from A to B, this gives me a group homomorphism. Let's say phi star. Group. Oh, semigroup. Morphism. I mean, the definition, you just send the class of P to the class of phi.
So unital semigroups always, no?
Unital.
You mean 0?
Yes, sure.
It's a monoid, not
Yes.
semigroup.
Yes, you're right. I mean, I don't know why the word monoid is not used in these. Why don't people call this Murray von Neumann monoid or the Kunz monoid, I don't know, but yes, it's good one. Okay, so that's the first property. The second property is homotopy invariance. Meaning that if phi is homotopic psi as maps from A to B, in a sense which maybe you can get what this means precisely, then they induce the same map. Next, it's additive. So the semigroup of a direct sum is a direct sum of the semigroups. And lastly, it's continuous with respect to inductive limits. I mean, semigroup inductive limit AI is the inductive limits of the AI, and with connecting maps being obtained by this functoriality. All right, so finally now I will define for you what the K0 group is, and it's a little bit subtle. You first define it in the unital case, and then I'll comment on what you do in the non-unital case. And it is, as I said, just the growth in D group obtained from this semigroup. So if A is unital, A0 of A is the abelian group generated by B of A. And by which I mean this growth in deconstruction. So it is, in other words, the set of, you can think of it as formal differences, such that P, Q are in projections in M infinity of A. Or the compact, you get hypothetical objects.
So this is the description of the growth in deconstruction.
Yes.
Provided you have cancellation.
Well, I'm not finished yet. So with P1 minus Q1, we declare this to be equal to P2A. You may object to the way of it, but I hope you know what I mean. So P2 minus Q2, if and only if there is some class R such that, I would like to say that this just means that P1 plus Q2 is P2 plus Q1, but precisely because I might not have cancellation, I have to allow for this extra ingredient here. So such that P1 plus Q2 plus R is P2 plus Q1 plus R. Okay, and then just as mentioned, for this unnecessary, precisely when I do have cancellation. Right, I mean, because without cancellation, I cannot deduce from this that Q2 is Q. Okay, so let me now describe for you a class of C-star algebras in which I do have cancellation, and that is indeed any algebra of what's called stable rank 1 that I mentioned a little after when I was having this discussion. So proposition would say, I'll give you some examples of K0 groups shortly. So proposition, if A has stable rank 1, stable rank 1 means that the invertible elements are dense. This means that GL So the invariable elements, let's say A might be non-unital, is dense in A. So if A has stable rank 1, it is also this holds, for example, for any finite dimensional C-star algebra, or also for limits of finite dimensional C-star algebras. So any AF algebra. So if this holds, then I have cancellation.
What do you mean by linear G, inverted linear
Yes, sorry.
dancing?
One.
Sure. Yes. Okay. Yes. Sorry. My lazy notation. So there should be dense in the minimal utilization. So this implies that P of A has cancellation. And in fact, a necessary condition for having cancellation is that A has to be stably finite. Right. Again, it's not hard to show just for reasons of time. I'm not going to get into it. I'll just say, for example, if A is continuous functions on X and X is 0 or 1 dimensional, then I have stable rank 1. Right. So this includes finite dimensional C-star algebras, for example, because I don't change the stable rank by passing to a matrix algebra. I don't change the property of having stable rank 1. Or in fact, it's a very non-trivial theorem that anything that's set stable and has a trace is automatically stable rank 1. So this is a theorem due to Michael-Redam in the unital case, and by some other authors in the non-unital case. So if A is simple, stable finite and Z is stable. A is simple, Z stable, and stable finite. Then stable rank A equals 1.
There are no two-dimensional spaces, compact spaces that C of X is stable rank 1.
I mean, this maybe requires a little bit of thought, but it's not particularly deep. It just follows really from the definition of approximating elements by invariable ones. I mean, what you can say in general, I mean, there is a stable rank is by its name a kind of rank. It is a kind of dimension theory. It makes sense to speak of stable ranks higher than 1. And there is a relationship between the stable rank of C of X and the dimension of X. It's something like half the dimension, something like this. But it's not a deep fact, but it requires a little bit of thought. Okay. All right. So that's so all of this. The take-home message for this is that in the stable rank 1 case, so in particular, in the classifiable category, when I have traces, then I have cancellation. So I don't need to worry about this part in the definition of K0. Okay, which I just remind you is the Grothendieck group associated to this American template. All right, so without the unital C-star algebras, now let me tell you how you define it in non-unital case. You do it by unit type, but it's a little bit subtle. So if A is non-unital, and I'll also explain why you need to do it this kind of subtle way shortly. So then K0 of A is defined to be the kernel of the map pi star from K0 of the unitization to K0 of C. So where pi is just the quotient map from the unitization to the complex numbers. So I have this short exact sequence 0, A tilde, C. 0 is pi. And pi star is just a map it induces. So, and pi star. Okay, so a general element in this K0 group is a difference of projections.
Unitization that means just attaching.
I mean the minimum unitization.
Well,
Minimum. Yeah, I mean the minimal unitization. Yeah. Okay, so and this is defined to be IP minus pi. Okay, so I mean, in other words, it's defined so that when I apply the K0 map to this, I get something exact in the middle again.
And maybe you should remark that an A is unital, you recover the usual definition.
Yes, I will. I was going to make that comment, but
it happened for more.
yeah, that's a good point. So, and that is a point that should be made. So if it was already unital and all right, okay. So all the time I've been saying minimal unitization because that's just what it means really. But even if, let's say, it was unital and you added a unit to it and you did this construction, then yes, you still get an isomorphic object. So this has no effect if in any case, if it is unital, if you're not taking the multiplier across.
And it's very simple because the minimal unitization gives you this A tilde as A plus complex numbers as algebras.
Yes.
So then you have decomposition and you see that the kernel is exactly K0 of A.
Yes, exactly right.
And it's if and only, I mean, A is unital if and only if A tilde is equal to A plus complex numbers as algebras, right? Not as vectors, right? Yeah.
So we,
For these multipliers, first of all, typically there's no pi.
Yeah, unless the map is non-degenerate, which I guess it would be in this case because it's surjective, I guess, in this case.
but we don't need this.
No, I'm talking about these multipliers. If A tilde
Yeah, you're right. Yeah, he's right.
if A is non-commutative, multipliers are even more non-commutative.
Now, unitization always has a character.
Yes.
And I see. I see what you're. I see it. Yes, that's true. I see your point. I mean, there isn't even such sequence. Exactly. Exactly. Yeah. Okay. Yes. Good point.
But we don't need cancellation here to write this as P minus Q, or it's automatic.
I mean, I guess I'm hidden in this is that this is well defined. Even if we don't have cancellation. Yeah. All right. And by the way, so I mean, this comes from the topological notion of K theory.
Because this difference is in the Grothendieck group.
Yes.
It's not on the level of real subtraction of something.
Yes. Yes.
Though the stability is needed really to make sense of the square brackets.
I mean, this is more generally true. I mean,
I think of difference.
Both.
Really, what I should be doing is I should not be writing the difference. I should be writing pairs.
Exactly. Yes. Yes.
And then
And the class.
exactly. Like modulo. Yeah. This is just sort of abbreviated notation. But yeah, really strictly speaking, I should be talking about this. Yeah. Okay. And this is a sort of a relative notion of K theory relative to the unitization. This comes from topology. Right? K theory of a locally compact space is defined relative to the one-point compactification. And then I would say that K0 inherits the properties of the V factor. In other words, it's functorial, homotopy invariant.
I did on the previous page.
Yeah, you're right. Yeah, exactly. These properties, exactly. Functorial, homotopy invariant, additive, continuous with respect to inductive things. All of these solve K0. Let me now give you a bunch of examples of K0 groups.
And it is worth mentioning that this fact is related to reduced K theory.
Okay, right, yes, yes.
Topology uses not only this projection, but also the splitting of this projection.
I see, yes, okay.
So we need two facts that you have this photograph sequence, but it's split by a homomorphism.
Yeah, right.
This A tilde.
Yeah.
Gives you also the splitting of this pi.
Sure, yeah, okay. Good observation, yeah. All right, so some examples. So, first of all, K0 of the complex numbers, it's the same as K0 of the n by n matrices, it's the same as K0 of the compact operators, and it's the Grothendieck group of the natural numbers, so it's the integers. Okay, I mean, all the time I mean isomorphic, right? K0 of is, on the other hand, 0 if H is infinite dimensional. The reason for this is that if I take any projection in B of H, then P, the diagonal in M2 of B of H, P001, is equivalent to 0, 0, 0, 1. I mean, because they're both projections with the same dimensionality of the range, infinite dimensional range. So this means that P plus 1 is 0 plus 1 for these.
Do we know cancellation for B of H?
We don't know cancellation, but even so, I leave it as an exercise, but still, this shows that.
It's on the level of V of A.
Yeah. P is 0 in yeah. So if it's finite dimensional, I get that. If it's infinite dimensional, I get 0. Topologically, I mean, the way this is defined is that K0 of C of X is the topological K theory of the space X. If X is compact Hausdorff, even if it's locally compact. K0 of the car algebra. Right. So the R algebra M to infinity is this algebra M2 sitting inside M4 sitting inside M8, and it's all the time this doubling up. Every connecting up is like this. So by continuity, this K0 function, this is K0. That's right. So K0 of this inductive limit is the inductive limit of the K0s. So it's the inductive limit of the sequence at each stage it's Z, and then at each connecting map, this is a multiplication by 2 map. And this is the ring of integers with a half adjunct. You can make a similar argument in general for UHF algebras. So for example, the K0 of the universal UHF algebra is the rational numbers. Okay, maybe next example is that K0 of any cone, by cone I mean C0 of the half open interval into A. This is called the cone over the C0 algebra A is 0 for any A.
By the way, I have to warn you, George just signed up.
I see, it's watching. Okay, well, good to know. Hello, George. Right. So this is true.
This is sort of a reduced cone. Oh, a reduced cone of A.
Okay. Fair enough. But I would just refer to this as the cone. And this is 0 because this algebra is null homotopic. So this is homotopic to 0. So this is the 0 C-star algebra. So by homotopy invariance, they have the same K theory. And then maybe last example I mentioned is that, again, by homotopy invariance, if you like, if X is a contractible compact Hausdorff space, then this is homotopy equivalent to a point by definition. So it has the same A theory as functions over point, which is complex numbers. So it's the integers that if X is contractible. So here's the one, I think, good reason for defining K0 of the non-unital algebra in this kind of subgroup. So let's just go back to the way I defined it. So I said you have to do it relative to the unitization. You take this kernel, making this sequence exact at the level of K0, or exact in the middle, whatever. I mean, you could think, well, why don't I just do the same thing? Why do I make this distinction between unital and non-unital C-star algebras? Why don't I just define K0 of any C-star algebra, unital or not, just to be the Grothendieck group of the Merry-Von-Neumann semi-group? Here's one possible answer to that. It's because essentially we want to get a well-defined, well-behaved homologic theory. So here's the theorem. If I have an ideal in the C-star algebra A, then, okay, so I have an ideal. So I have this sequence 0 J A open J 0. So let's say this is iota inclusion map I the quotient map. So I know K0 is functorial. So this induces a sequence at the level of K0. So then the sequence K0 of J. So this is iota star, 0 A. This is I star, 0 A is exact in the middle. All right. I mean, if indeed, in the non-unital case, we define K0 so that this is true in the special case where we have the algebra A sitting inside its minimal unitization. But I'm claiming that in general, if I have any whole idea sitting in A. I mean, I'm not at all going to prove this for you. I'm just telling you this is a fact. And I'm also going to tell you that if we don't do this slightly subtle definition of K0 in non-unital case, this is no longer true. We don't have this as a fact. And we very much want this to happen because we want to get long exact sequences, essentially, from this. This is what I mean by a well-behaved homology.
Also, maybe it's worthwhile to add that indeed to have Search-Swan, you need compactness. Right? I mean, if you really want to have vector bundles given as finely projected modules, we need compactness. And that's why it's completely natural that when you go to locally compact, well, it's minimal 1-point compactification. Then you look at vector bundles on right compact ways,
Yeah.
and this comes to your K0.
Sure. Yeah. Yeah. Fair point. Okay. So as I said, this is true with the right, quote unquote, right definition of K0.
Yeah, so, but your question was philosophical. Okay, why non-unital are needed? But the point is that this fact could be rephrased in terms of unital algebras. If you take the minimal unitization of this ideal, then you can, instead of speaking about the short exact sequence, you can speak about the square
Open diagram.
Yeah.
Okay. Yeah.
So.
Okay. So I take your point. I certainly take your point.
On the other hand, this short exact sequence means the short exact sequence of vector spaces, algebras,
right?
Because the category of algebras is not abelian.
Yeah, fair point.
But if you think in terms of this pullback diagrams, it is better.
What is an abelian? Sorry, can you repeat?
The category of algebras.
Algebras is not abelian. So the notion of an exact sequence doesn't make sense there. You are forgetting the algebra structure. You remember that these iota and pi come from non-unital algebra maps,
Mhm.
but you are speaking about vector spaces, plain vector spaces.
Right. Yeah, okay, I mean, I do take your point.
By the way, it's a very beautiful argument of Attia Hirzebruch, which tells you how to get out of this usual short exact sequence. So in terms of topological spaces, you have a composite space, you remove a closed subspace, and then you have this exact sequence for vector bundles for K groups, right? But there's a very, very beautiful argument where you can change it into everything being compact. And it's very geometrical. You use homotopy invariance, you use many arguments, but then you out of the usual 6-term exact sequence for K theory in the commutative setting, I'm talking about you can actually derive the Meyer-Vittori's exact sequence for commutative sister algebras. And the argument of Attia is so beautiful, so that actually we managed with Paul Baum to generalize it to completely arbitrary sister algebras.
I see. Right. That's very interesting. But speaking of this 6-term exact sequence, let me.
Yeah, that's what we are driving at.
So first of all, so I said we want to get a long exact sequence of K theory without any to tell you what the higher K groups are. So for n bigger than or equal to 1, we define the higher K group K and A to be K0 of the suspension, which is by definition the tensor product of A with continuous functions on Rn vanishing at infinity. The theorem is that if I have an ideal, then we get a long exact sequence. So then there are connecting maps delta from K n, I guess, A over J to K n minus 1 of J, such that there's a long exact sequence dot K n J. So this would be delta A n let's see. The end, the long exact sequence is so K1, A1, A over J, delta 0, J 0, A 0, A over J. Now I jumped the gun slightly. I mean, I slightly did in my notes, but whatever. Okay, here is the I guess what I wanted to tell you, which I was telling now, is that K1 has another description, not just in terms of K0 of this suspension of K0 of A tends to C0. We can define it very much like the K0, except with unitaries instead of projections. So maybe I'll mention this now. So here's a fact theorem. Let's see, theorem. It's not, again, it's not difficult to show, but just for time, I won't get into it. So K1 of A, which by definition, as I defined on the previous slide, is K0 of A tends to C0 bar. It is, on the other hand, isomorphic to the abelian group generated. So it's another growth and deconstruction by homotopy classes of unitaries. In M infinity of A.
You mean 18?
Well, what I would say is that in the non-unital case, we do a similar relative construction as the case here. Maybe I'll say that. So similar relative definition or non-unitally. So relative to the unitization.
But wait,
Are you sure you don't do anything else anymore? No, it's just like the unitized in a tilde.
Well, it depends on how you want to approach it. You can define K1 to be the K1 of A tilde if A is non-unital, or you can define it in this relative way and it will turn out that it's isomorphic to K1 of A tilde.
yeah, but the point is, what's the unitary in the non-unital algebra?
This is what I mean by relative.
Units to,
Yes.
to this infinity of A.
Yes. What I'm saying.
So adding this tilde to A is not enough because it will be still non-unital. Okay. M infinity.
M infinity of A tilde.
Yes, it's still non-unital. No,
Why? I see. I see what you mean. Yes. Okay. Yes. Okay. Yes. Okay. Let me be more precise. Let me say unitaries in Mn of A for n in n. Yes. Yes. It's locally unitals. Yes.
Yeah, and in fact, it's very important in proofs to, that you can say, so I have a homotopy, but there always exists like that because of compactness of the unit integral.
Yes.
So there is the maximum number n, but you never leave this m and n.
Yeah, absolutely. Yes, that's right.
sorry, but now this A needs this tilde.
Yes. So, okay, what I'm saying here is, if A is unital.
Okay.
Yes, but what I mean by this.
Yeah.
No, okay, no, yeah, let me say clearly what I'm trying to say. What I'm saying is that this is the case if A is unital. And if A is non-unital, K1 of A is isomorphic to the kernel of this map. So from K1 A tilde to K1 C.
Which is 0.
Which is 0, yes, which is 0. So this is why it'll turn out that it is in fact isomorphic. So in fact, but I mean, we don't know this is 0 to begin with, but yes, it is 0. So in fact, K1 is 0, as pointed out. And
That's my whole remark. I mean, just a tilde. That's it.
K1 of A. Yes, okay, right.
I know what I was saying.
I hope it's clear now.
Yeah.
Right. So it is a abelian group with operations. So with the 0 element is the class of the unit in A, and the addition U plus V is equal to, in fact, the product U V. But in fact, this is the same as UV1. I mean, that's not immediately obvious, but a similar, but here's 2 by 2 rotation here to show you that you can rotate this V up to U. So in fact, what this shows is that the inverse of U is U star, because then U plus U star is 1, which is 0. So this
More important trick is this another twist which shows that it's abelian because we are using
that's a absolutely good point. Yeah, no, that's an excellent point. Yes, indeed. Yes, this shows that it's abelian with this operation I've defined it that way. Yeah. So in fact, this means that I can think of elements in this abelian group not just as formal differences, but I can think of them as classes of single unitaries because, you know, so what this tells me is that U, a formal difference U minus V is in other words U plus V star. So it is U V star like this. So I can, elements in this abelian group generated by unitaries are represented by, in fact, single unitaries, not these formal differences. Okay, so all right, so I think typically it depends on what you're trying to do exactly. But typically, when one thinks of K1, they think of this as the group of homotopy classes of unitaries in the algebra. That's what people think about when they think of K1. So let me mention some examples. So I already stated one, that K1 of the complex numbers is 0.
Coming back to your long exact sequence.
Yes.
I have to say something. Usually long exact sequences are infinite in both directions.
Yes, fair enough. Yes.
Only long exact sequence, yeah, one side.
Yeah, sure. Yes, that's true.
For extensions and closing these to the distinct exact.
Yeah, which we'll do.
This is a matter of completely different story.
Yeah, that's a fair point. Okay, so first example I already mentioned, K1 of the complex numbers is 0. In fact, K1 of B of H is 0 for any H. I mean, so this includes, if I take a one-dimensional Hilbert space, this includes K1 of C is 0, also K1 of Mn is 0 for any. And the reason is that I have Borel functional calculus. So in B of H, I can, by taking a logarithm, I can find a path from U to the identity. So the class of any unitary is 0. So this is by Borel functional calculus. Because I have this continuity under inductive limits. So this in particular K1, as I said, Mn is 0. I have additivity. So K1 of any finite dimensional Caesar algebra is also 0. I can take limits, which tells me that K1 of any AF algebra is 0. K1 AF is 0. In fact, also K1 of AI. So AI, remember, these algebras look like limits of continuous functions from the interval to some matrix algebras. But what I said that we have homotopy invariants, remember? So this is contractible. So the any K0 or K1 or any IFK group of an interval algebra is the same as that of a point, which is 0. So for AI algebras, I also get K1 group of 0. And K1 of continuous functions, let me in fact say that K1 of A is, so if my algebra is stable rank 1, remember that meant invariables are dense in possibly in unitization, then I don't even need to pass to matrices. So the K1 group of a stable rank 1 algebra is just the group of homotopies of unitaries in A. Like I'll write like this: UA modulo those that are connected to the identity. So if A is stable rank 1, invariables are.
You're using the fact that stabilization commutes with reflection.
Possibly, I'm not sure.
Well, K1, I mean, you define K1 as the suspension of A, so it will be the tensor product with C naught of R. But then we are saying that
I'm not saying it's true in general. I mean, this very much needs stable rank 1.
okay, but if what I'm trying to see is the following. Let's see A is of stable rank 1.
Yeah.
Okay. So now when I take the suspension of A, is it again of stable rank 1?
Maybe not, because if I think of it something commutative, tensouring with C0 bars, so I'm tensouring something one-dimensional.
Yes.
Like,
You mean suspension? This is like taking two-dimensional sphere, for instance.
yeah, exactly. So I could get something higher than.
I mean, this reduced suspension, just tensoring in C naught of R.
But then I can get
Never.
dimensional.
You can construct something two-dimensional.
Exactly.
So the rank for sure is not.
Okay, so I missed something else.
I mean, this is a fact that I'm telling you, it's not immediately obvious.
Okay. Yeah, I just tried to see it trivially, but it's not.
Yeah, it's not. Okay. So in particular, an example of a stable round quantity star algebra, it indeed continuous functions on something one-dimensional. So for example, the circle. So what this is saying is that K1 of C of S1 is the group of homotopy classes of unitaries in C of S1. Okay, what's a unitary in C of S1? It's a continuous function from S1 to S1. It's a unitary valued continuous function. So continuous function from S1 to S1. How do I know the homotopy class of such a thing? It's the winding number. So this is the isomorphic to the integers by the winding. Yes. By the way, the K0 group of this is also Z, just generally provided the trivial bundle. I don't have any interesting things apart from that going on. Okay, so that's it for examples. Now let me address this point that was made about closing up this following exact sequence. It's really a 6-term exact sequence by what periodicity. So there I'm.
So both periodicity used for two purposes. First, to extend this sequence indefinitely.
Sure. Yeah.
Second, to close it into.
Yeah, absolutely.
Experiments.
Yeah, exactly. So there's an isomorphism. Isomorphism. The bottom up, which I will not have time to define for you, from K0 of A to K2 of A. Okay, so I mean, this is why I just focused on the end of the sequence, the K1 and the K0, because when the next level to the left would be K2, but that's now isomorphic to K0, so I can loop it back around. So the long exact sequence gives me the 6-term exact sequence of A theory. I have on the top 0J, A0, A over J. Oh, sorry.
Post direction.
Does it matter? I guess.
What do you mean?
Does it matter? I mean,
Because okay, you don't have yes dots before.
right. One, J. Over J. Okay. And these connecting maps, I will describe in a little bit of detail. This is called exponential map, and this is again denoted by delta. And these maps represent obstructions to lifting things. So this exponential map kind of tells you the failure of this map to be surjective. So this exponential map represents the obstruction to lifting projections from a quotient to the algebra. Similarly, this is the failure of this map to be surjective. So it represents the obstruction to lifting unitaries from a quotient to the algebra. This is how you should think of these things. Let me briefly tell you how they are defined. So this first of all, this exponential map, it's defined like this. So X is defined on K0 of the quotient. So its input is a difference in projections where these P and Q are in some matrix algebra over the quotient. Okay, as I said, we can't in general lift a projection to a projection, but we can lift to a self-adjoint element. So you find some self-adjoint element X that lifts P, some self-adjoint element in A that lifts P, and you find some self-adjoint element Y that lifts Q, and you define this to be the formal, so we're thinking of this as a formal difference of unitaries, positive unitaries. So this is class of e to the 2 pi X minus e to the 2 pi Y. So X lifts P, Y lifts Q.
And please correct me if I'm wrong, but I guess I can just compute this map by saying first I go by this block natural isomorphism to K2 of A mod I, and then I have connecting homomorphisms from K2 of A mod I to K1 of J.
Yes.
Or JS.
Yeah, exactly. And then if you unpack that, then you use the bot isomorphism, this is what it amounts to.
That's very important. I mean, this map is given by the bot periodicity. The other one works in algebraic theory.
Yeah, absolutely. Yeah, exactly.
I have some terminological problem here, because classically it was that first by using the suspension, people defined the negative K theory,
Right, yes.
Like Karup.
and even before Karup's.
Okay, yeah.
But after using dot periodicity, it was even defined for positive
Okay,
K theory.
okay.
So I don't remember, your indexing was, you started from positives.
Yes, I just defined it for positive elements, yes. Which I suppose one would expect the way things work from commutative to C-star algebras being contravariant. So instead of a cohomology theory, we're getting a homology theory.
In fact, it's not a homology theory.
It's an extraordinary homology theory.
But not extraordinary.
Is it not? I mean, it's
No, it's not, because the argument of this is an algebra, okay? But it doesn't satisfy any axioms of homology theory. Resembles this, I say, using periodicity, but the beginning was that first, if you are using suspension,
Yeah.
okay, then you have a map between, no, you have negative K theory. Only dot periodicity allows you to define positive.
okay, yeah.
It's not only a few convention, it's something deeper here.
Yeah, okay. I mean, fair enough. I'm willing to accept this, but from now on, I will never speak about higher K theory other than K0 and K1. I hope I don't eat my words there. And I will all the time be talking not about this long exact sequence, but the 6-term exact sequence. Yeah. Okay, so this is this exponential map. Let me briefly describe to you the other map, this delta, and it's going to be defined like an abstract Fredholm index. So delta abstract. I'll tell you one way that's equivalent, and it's sort of it's not actually how it's defined, but it's equivalent to it. So abstract Fredholm index. All right, let's just go back a second. So it goes from K1 of this quotient into K0. So I need to tell you what it does to a unitary. And what I will do is take a unitary in A over J. I can lift it again, not to a unitary, but I can lift it to a partial isometry, maybe going to a bigger matrix algebra. And then I just take the suitably defined index of that partial isometry. So, so given a unitary U in some matrix algebra over A over J. So there is partial isometry. V in some potentially bigger matrix algebra. Such that, and again, this needs proof, but I'm telling you it's fact, such
A. In A, right?
Yeah.
Yes,
A.
sorry, yes, thank you. Okay, so such that.
There's a part of isometry in MK away. It's also part of MK away, not Czech.
Yeah, but I certainly guess
That's not what you know.
so there I is the quotient of A over J. But then I define delta of U. Again, so remember I said that K1 classes can be represented by a single unitary, and this is by definition the class of 1 minus B star B. So one, the identity in the, and this is living in A tilde minus 1K minus C B star. And you need to show that this does make sense, and it does give you an element of K0 J. So it does live in the suitable kernel. Okay, so I mean, I'm just telling you as a fact that this is how you can compute this delta. Let me show you an example in practice. So let's compute the K theory of the Tiflitz algebra. So the Tiflitz algebra featured quite heavily in a few weeks ago. So yeah, let's see how we can use the 6-term exact sequence and actually this formula to compute the K theory.
I can just write it graph and use reference lines and we don't.
Yeah, sorry, just good. Right, so example, Tiflitz algebra. Okay, so I'll just say it's given by this extension, compact operators, Tiflitz algebra, continuous functions on S1, 0. So this is this symbol map, and this is generated by the unilateral shift. Unilateral shift. All right, so we're going to apply the 6-term exact sequence with J is compact operators, A is the Tiflitz algebra, and A over J is C of S1. So we have this exact sequence, K0 of K, K0 of T, K0 of C of S1 from the top, and then K1 of K, K1 of T, and K1 of C of S1. Okay, well, we know what some of these things are. So K0 of K is the same as K0 of C, it's just Z. And then K0 of T. Then K0 of C of S1, I mentioned, is just, again, Z, just generated by the trivial bundle of S1. K1 of K is 0, it's the same as K1 of C. So this is 0. And then we have K1 of T. Then we have K1 of C of S1, which we described was also Z. And then we have this map delta. All right, so let's see what this map delta is, and then we'll be able to compute K0 and K1. So delta, let's see what it does to 1. So delta of 1. Okay, what is 1? What is the generator, in other words? So what's the take that has winding number 1? It's just the function Z versus Z, it's the identity function. Class of the identity function. Then what did I have to do? Let's go back briefly to the definition of delta. So I took a unitary, I found some partial isometry lift of it. The partial isometry lift is, of course, this unilateral shift. And then I compute the class of 1 minus SS star minus class of 1 minus S star. So this is the class of 1 minus S star F minus 1 minus S star. So this is living in K0 of K. So it is Z by the rank. So I just need to know what the ranks of these operators are. But S is isometry, so 1 minus SS star is 0. And 1 minus SS star, you can show it's rank 1. So this is rank 1. So delta here is an isomorphism. All right, and then you just here we go. This is an isomorphism. Okay, so what does this mean? I mean, the kernel of this is 0, so that's the image of this. So K1 is 0, and then similarly, K0 is Z. So K1 of T is 0, K0 of T is Z. Right.
You can conclude even more, but it's Z denoted by 1 in the.
Yeah, exactly. Yeah. So I really just wanted to illustrate that this is not just some abstract nonsense. I mean, it really is useful. You can get your hands into the 6-term exact sequence, and you compute with these maps, and you can learn what the K theory of some very natural system algebras. So I will mention, maybe for time, I will not go through the computation. So another example for which you can do a similar sort of procedure is this. Oh, there is a limit of some sort.
Oh, no. What is on the subtract?
Ah. No, that's amazing. I mean, I've never. I knew it was a finite number, but 20.
This some comment about if I've been going overboard. I don't know. What does one do?
Maybe you could be periodically. To the left, to -1, to -1.
We are bad with this, you know, negative K here. Well, I guess the only thing you can do is to go to page number 1 and erase it. I mean, because I honestly will not find a quick fix.
So is this? Is what happens to go back? Yeah, okay, okay. Geez, I apologize for my verboseness, apparently.
I'm completely shocked. Why is it?
All right.
Clear.
Clear, yes, good, thank you. I hope this,
All drawings.
it's not gonna just this page, we'll say.
Oh, no.
Okay.
So that's exactly, you know, what periodicity, 20. Let's go back.
Yeah, that's right. Take your inaction.
Blackboard period.
I think also in general, if you press select, you can, like, this board is not just this. I think this whiteboard on Zoom is just, you can, yeah, like, you can try that.
So if I do,
Yeah.
where's select? Select, and then
just try to. No, it doesn't work. Okay.
I thought it would just go down.
I think it would.
So I would have like infinite space between page. I see.
But I don't know.
Scroll bar to the right.
Oh, just.
No, don't touch it. Don't touch it.
We can invest in it.
I've never seen it before.
I feel rather embarrassed about that.
No, we discovered the phenomenon.
Okay. I will just mention, without actually doing the calculation, but it's a very good exercise, I think. If you're a student trying to learn how to compute with K theory, it's a good exercise to fill in the details here. So the dimension drop algebra, let me remind you, is this C-star algebra. So it's continuous functions from the interval into MP tend to MQ. Such that at 0, it's in this block of P by P matrices. And at 1, it's in this block of Q by Q matrices. All right, so what you do is you use this ideal, J, to be the ideal of functions vanishing at the endpoints. So C0 of open 0, 1 into MP tends to MQ. So use this ideal and then use the 6-term exact sequence and figure out what these maps are, and you will show that. You can do this whatever P and Q are, if they're co-prime or not, but in the case where they are co-prime, it works out to be something quite simple. So if P and Q are.
There's the suspension of MP tensor MQ, right?
Yeah, yes, yeah, and in fact,
Well, it is from 0 to 1 without 1.
Yeah, I know.
Yes.
So that's why the suspension.
Okay, suspension.
It is exactly this suspension. And in fact, that's a crucial part of the calculation. Use the
suspension. For the common, yes.
Yes.
So if the highest common factor of P and Q is 1, then the K0 group of this algebra is generated by the class of the unit, and it's the integers. And the K1 group is 0. So if P and Q are not co-prime, you get some cyclic group there. And here you still get Z, but it's not generated by the unit. The class of units is R, where R is the highest common factor. Okay. So, but as I say, I think this is an excellent exercise to try. See if you can fill out the details. So, by the way, from this, I said that the construction of the Jiangsu algebra, it's an inductive limit of these things. So by the continuity, this tells us that the K theory of, so this, in other words, notice it's the K theory of the complex numbers. So the same is true for the Jiangsu algebra, the limit. All right.
So can I have a quick question?
Yeah.
So why this co-prime matters here? So
Well, it's as I said. I mean, you can do the computation, the same computation, even if they're not co-prime, but you won't get these answers. So if P and Q are not necessarily co-prime, and you really just have to sit down and do the computation to understand why this is, you still get Z, but it's not generated by the class of unit. The unit represents some, not the class of one. It's not one, where R is the highest common factor, and K1 is not zero. It's some cyclic group, depending upon the highest common factor. It just it comes out of the complex relation.
okay, so
Similarly, as you did in the case of the Kepis algebra.
Yeah, yes, except actually. In fact, here it's what's not, in fact, the exponential map is what's going to be crucial here for this computation, not the delta map. So it's an even better exercise. This will give you some practice for the exponential map. Okay. All right, what I want to do in the remaining.
What do you mean by class of one? Just recall me because I'm a little bit.
So one is a projection in this algebra.
But this.
Yeah, so I guess I mean should be squared.
Identity for the class of
The identity projection, the constant P times Q identity matrix over this interval. Yes, that's what I mean. Yeah, sorry, but this is. But thank you for the question. Okay, so what I want to do now is just mention one more example. And then in the last 15 minutes or so, I want to talk very briefly about the UCT. Okay, so the example I want to mention, here another page. Yeah, just bigger. All right. So at the moment, we have this K0 functor. It's not at all clear.
But can I just,
Yeah.
what is the generator of the set in that case, actually, in this Jacelon algebra?
It's also one.
Also the class of the,
Definitely it's one.
yeah, it's the class of the.
That's the point. It's really like complex numbers.
So in fact, something really strong is true. So these algebras are projectionless. The only non-trivial projection is the unit. So in fact, any star homomorphism from one of these, I mean, that's true if P and Q are co-prime. So any star homomorphism from ZPQ to ZP prime Q prime is automatically unital. So the unit of each of the, and that follows because it's projectionless. There's no other thing that the unit can be sent to. So any non-zero star homomorphism has to be automatically unital. So this inductive sequence of these prime ZPQs, it's unital. So the unit gets mapped to the unit, gets mapped to the unit, gets mapped to the unit of Z. So this continuity here is not just preserving the limit of groups, but also the unit getting mapped to the unit all the time. So it's a unit.
So at the level of K0 in the system, you have identities.
Yeah, yes, exactly. Yes. All right. So what I'm saying is that at the moment, I have this functor, but it's not at all clear why should this be something that should classify theta algebras. Maybe you can believe that in situations where I have lots and lots of projections, for example, AF algebras, then yeah, there is a good shot. But it's at the moment not clear beyond this case, really. But one thing we can say straight away is that because it's a functor, we can use it to distinguish isomorphism classes. So we know that if two algebras have non-isomorphic K groups, then they cannot be isomorphic, because an isomorphism at the level of the algebra would induce an isomorphism at the level of the K0 groups. So, okay, so I'm going to describe for you one such situation where we can deduce non-isomorphism of C-star algebras. And it's, I want to think of this as a topological analog might be something like, how do we know that Rn is not homomorphic to Rm if M is not equal to N? It's not exactly trivial. You need to use homology, or maybe not need to use homology, but that's one way to look at it, right? We get different homology groups if we take their point in the sphere, so they're not homeomorphic.
No. That's not with Rx.
So I'm going to present to you something similar. Let me mention that the free group factor problem is perhaps the big open problem in all of operator algebras. So is one of the major. So, and the question is, if we take a free group Fm on M generators, we take the von Neumann algebra generated by this. What I mean by this is, we take the group ring C Fm, and we take, let's say, the left regular representation. So on the Hilbert space of L2 of Fm, and then we take the closure in the weak operator topology. So this is what I mean by the von Neumann algebra associated with this free group. So the question is, if I do this construction on Fm and I do this construction on Fn, do I get isomorphic von Neumann algebras? So if M is not equal to N. So this is open problem, and like the open problem in operator algebra. But the point I want to make is that the corresponding question for C-star algebras is easily answered using K theory. Yeah, so the C-star version is easy. Well, relatively easy. And that is because you can show that K0 of, okay, well, when I say this, the C-star equation here, we need to be clear what I mean, because unlike the von Neumann case, we have different C-star completions we can take, but it is true whatever. So the reduced group C-star algebra of Fn, the K0 group, is in fact the same as the K0 group of the full group C-star algebra. And it is Z. Okay, so at the level of K0, we can't distinguish them, but K1 is Z at the end. So K1 is what distinguishes. K1 C-star
And it's generated by the generators of the free group.
yeah, exactly. K1 C-star.
You forgot about the M.
I forgot about M.
M at the beginning.
First N is N.
K0 C star are Fm. Is isomorphic to K0 C star Fn.
I mean, what you wrote is true, but it's identity.
Yeah.
No, it's not identity, it's uncanity.
No.
I want to build one is yes.
Are reduced.
Yeah.
It follows from this that if for M and N is.
Yeah, but
No, but the point I was making is that for the reduced, same as the full.
That's max.
so we are not comparing for two different and
No.
yet.
Not yet.
Okay.
Now that I know this, I can compare.
Yes, and then yes, you can.
The reason I'm telling you this is because one of these computations is easier than the other. It's pretty easy to show that the K theory, the full group C-star algebra, it is given by this. You need to do a little more work to deduce it for the reduced group C-star algebra. I highly recommend, so my PhD supervisor, Simon Batham, has some notes on exact C-star algebras where he goes through a sort of elementary computation of this. Anyway, whatever. So as I said, the C-star version, we know the answer is no. We're not isomorphic.
Sorry, so here you have the universal C-star algebra.
Yes.
How can you use this to say anything about this version von Neumann version?
You can't. That's what I'm saying. The C-star version of TC. Yes. Yeah. And by the way, I mean, we can't attack this problem similarly because the K theory is the same. This is a free group factor. It's a von Neumann factor. So the K theory, I think, will just be the real numbers. It's just the projections are indexed by the values, the trace values. So these are a continuum. So we cannot distinguish these by K theory. So the only point I'm making is that at least for the C-star,
What is the value of this easy analog of something which is different?
I'm not claiming that this sheds any light on this. I'm just introducing you.
Maybe not of this, but what is the status of this claim? Why you started from this von Neumann open problem?
Because I was telling a story. I thought it'd be entertaining to you.
That's it. Okay.
I thought I was weaving a tale and telling you about
Something easy, apparently similar to something deep, something. Okay.
yeah, I'm just telling you, I thought I was being dramatic. I don't know. I'm insane.
I'm amused. Okay.
Okay, good. This is my goal.
Roll back. Thank you.
Right.
Yeah, you're always assuming end to finance, right?
Yes. Yeah, I suppose. So. All right. So, but anyway, the point is we can use K theory to distinguish that. Let me in the last 10, 11 minutes or so, at least start telling you about the UCT.
So before you go to UCT, can you still go back for a while to these to this cancellation property? Because you gave us nice examples, but they're very sort of topological, non-geometrical.
Yeah.
And I just, before I ask a question, let me make a very quick comment. This is a beautiful theorem by our father, Mark Riefel, that you have cancellation property for the irrational rotation sister algebra, the landmark of.
Yeah, okay, sure. Yeah.
This is a very difficult theorem of Riefel. And he would often complain that the technology he used to prove a cancellation property for this non-commutative torus sister algebra, irrational rotation sister algebra, is completely different from the way you prove it for in the classical situation.
I see.
So you also have cancellation property for a classical torus in the commutative sister algebra,
Yes.
but these proofs are completely disjoint. Which is kind of funny because one is you have a continuous field of sister algebras, one is a deformation of another. It's a Riefel deformation, right? But the proofs do not deform. And this cancellation property is true because of completely different reasons than it is true in the classical case.
And I suppose also the stable rank does not deform because the irrational rotation algebra has stable rank 1.
Yeah.
Sorry. So that would be another way of deducing that it has cancellation because it has stable rank 1, but I don't know.
But this is how we proved it probably by computing the stable rank.
I see. Of course. Yes, of course.
It's not so.
I mean, yes, I mean, of course, this notion is due to Riefel. This notion of stable rank.
Exactly.
Yes. It's a fair point. Yes.
Exactly.
I guess this is what he was developing his notion for.
Exactly. So this is why I thought it would be important to mention it.
Oh, yes.
And also our brother Albert Schuh, he has some remarkable theorems for cancellation properties for quantum spheres, and things are very non-trivial, very tricky, and very
right.
If you look in depth at cancellation properties for quantum spheres of different types, and
right.
There's but these are really spheres, sister algebras, which come from topology. And so it's really non-commutative topology, and then you have a lot of fun studying cancellation properties in K theories over there. And now I can ask my question. So this is a canonical, high school example that of the lack of cancellation properties, the real K theory of S2. But how about the complex K theory of S2? Do you have cancellation property for complex K theory of S2? So really the sister algebra. I keep on forgetting.
Yeah, I
know it.
Yeah. I mean, I would like to say yes. And that's my instinct to say yes, but
Come on, you remember? I just don't.
Probably yes.
okay. Yeah, I mean, let me think about this.
Because you have if you look at that, because you do it with a tangent bundle, right? On S2, but the tangent bundle is real. Yeah, exactly.
It's complex.
Yes, exactly. This is the Hopline bundle with winding number 2. Okay.
Yeah.
And then when you forget the complex structure in the Hopline bundle for winding number 2, you get on the nose the tangent bundle. This is a very beautiful exercise. So this is really funny because, of course, when you take into account this complex structure, the winding number classifies K0 classes of Hopline bundles, right? I mean, just winding number is equal to a K0 class. That's how we identify them with Z.
Yep.
So what projection is 1, -1, depending maybe on the convention. But then when you forget this complex structure, boom, I mean, this winding number 2 vanishes and you have something which is trivial in K0. So I would expect that you have cancellation property for S2 in the sense of complex vector bundles, in the sense of K0 of sister algebra.
Yes, I mean, I would also agree with this, but I can think about this and we can.
Yeah, but okay. Yeah.
Just also here, so other completions, other sister algebras for completions of group algebra of free group.
Yeah, it's a good question. Yeah, good question.
Yeah, I mean, very intermediate, but the question is what are they? Yeah.
Yes, I don't know if they are in any identifiable sense.
Yeah.
Maybe one thing I should mention is that, okay, I mean, these are different. The following group, they're not the same because this is a non-amenable group. I mean, this is the crux of the Banach-Tarski paradox. But in fact, so this is not a nuclear C-star algebra, but it is exact. But this is not even exact. This is what Simon Wasserman proved this, that this is not an exact C-star algebra. And that's how you know that B of H is not exact. Because B of H, I mean, exactness passes to subalgebras. So if B of H were exact, then every C-star algebra would be exact. And here's a non-exact one, B of H is not exact.
And also, since Ludwig mentioned Borsuk-Ulam, one of the incarnations of Borsuk-Ulam is the question of contractibility of compact quantum groups. So when you look at the compact house of topological groups, we have an old theorem telling you that the only contractible compact house of topological group is just a trivium. Okay. And we very much would like to prove the similar statement for compact quantum groups. And for us, when you look at this convolution C-star algebra of a free group, for us, it's an abelian compact quantum group. And exactly by this K3 argument, we could prove that it's non-contractible.
I see. Yeah. Okay.
But this was for Ludwig because he mentioned Borsuk-Ulam.
Fair enough.
But we are speaking about the dual of this.
Yeah, of course.
So how contractibility of this algebra is related to contractibility?
I'm not
of
again,
the
I'm
dual?
not saying that. I'm saying contractibility in the sense of a quantum space. This is a different story. I mean, I'm looking. This is convolution C-star algebra on a real group, but then by sort of contracting dual, I'm looking at the unit because it's a discrete group. Okay, and the C-star algebra unital. So I have a unital C-star algebra. So it corresponds to quantum compact quantum space, and I'm talking about this compact quantum space being contracted. Okay, sorry.
No, that's fine. I mean,
Come back to this. The two-dimensional sphere.
I mean, I don't know if you may come back to whatever conversation.
Do you know an example of a function on a two-dimensional sphere, which continuous function, complex value, which cannot be approximated by inverted functions?
I asked him around, yes.
Yeah.
I mean, I don't think it should be difficult to cook one up. I mean, on the spot, I don't think I can do it for you, but.
Okay, people know this example.
But you can cook it for dinner.
No, I'll set this as homework for myself, and we'll readdress the issue on Friday. But I really don't think it's difficult to cook it.
So it would be a very good pedagogical move to present it.
Yeah, fair enough. I think
Rank one.
I think on a disk, say
Even on the disk.
I mean, a disk does not have stable rank one continuous function on a disk. So yes, I don't think it's difficult to cook up this example.
But let's get it for dinner.
Yeah. But okay, I mean, I cannot talk about UCT in 3 minutes, so I think I will have to leave that for next time. So maybe let's think about what the plan is for next time. I'll start with this UCT. I'll just briefly tell you what it is and what kinds of C-star algebras it applies to. You know, the big open question is whether it mathematically applies to every nuclear C-star algebra. Maybe yes, maybe no. Yeah, maybe I will. Maybe after this, I will just move straight to telling you about traces. I think after this. Yeah, so I'll tell you about what I've been using these traces, tracial states all the time. I'll tell you exactly what I mean by this and what kind of structure the set of tracial states has. It's what's called a Choquet simplex. So I'll tell you a little bit about Choquet simplices, and I don't know, time permitting, I'll start talking to you about this Kunz semigroup gadget, which is this analog of the Merritt-von Neumann semigroup.
But guys, please do remember that Bhishan doesn't finish his lecture course next week. He has 2 weeks.
Yes, right. Yes.
So V continues after the level, so it's not V under the star.
Yeah, I mean, the plan is that this week is meant to be just background on classification, just introductory stuff. Just so you know what I'm talking about when I get to the real stuff I want to tell you about, which is the applications of classification. So that'll come in 2.5 weeks or whatever it is.
And isn't it the relationship between the UCT and the nuclear that is so difficult?
Yes, I mean, it's known, and I guess I'll mention this again on Friday, it's known that there is an exact C-star algebra that does not satisfy the UCT. This is an example of a scandal. That it's some kind of reduced group C-star algebra. So it really is a question about nuclear C-star algebras.
And of course, it's a reduced group C-star algebra, and this group is discrete or not?
Yes, I think so, yes. It is some sort of group of quaternionic isometries, something like this. I do have it written down somewhere. I mean, Nigel Hickson refers to it as a sobering example. Yeah, it's
Quite
so if
small group.
we have a discrete torsion-free finite co-volume subgroup of SPN1. So this is this quaternionic isometry group, and such a group.
Finite dimensional.
So a discrete torsion-free finite co-volume subgroup.
It's a lattice in.
Lattice, exactly. Yeah, exactly.
It's a plectic group.
Okay, so I guess it's good place to stop.
Yeah. All right.
Okay, thank you so much. Stop recording.